Welcome to lecture number 17. In the last lecture I discussed the standard T structure on the global stable homotopy category, which is made up by the globally connective spectra and by the globally co-connective spectra. So the equivariant homotopy groups vanish in all negative degrees in one case, and all equivariant homotopy groups vanish in all positive degrees in the other case. In this T structure, the heart is equivalent to the abelian category of global functors, and the equivalence is implemented by the functor pi0 underlined. I've now developed a lot of the basic technology around the global stable homotopy category, and I would like to now turn to applications and examples. I want to devote each of the remaining lectures either to an interesting example that I'm going to discuss in detail, or I want to explain a calculation where the global formalism is helpful in either coming up with the answer or in actually proving the answer. And sometimes we have both an example and a calculation. Today I would like to start with such an example, and this involves the symmetric product spectra. Let me start from the very beginning and remind you what symmetric products of spaces are. Here's the definition. The nth symmetric product of a space X is Spn of X. This is X to the n, the Cartesian product, and you're dividing out the action of the symmetric group that permutes the coordinates. So here I'm taking the strict action by the symmetric group, not some kind of homotopy action, and this is the quotient in the category we're working in, the category of compactly generated, including weak Hausdorff spaces. We will mostly be interested when X is a compact space, such as, for example, a finite dimensional sphere, and in that situation this infinite symmetric product is just the quotient space with the usual quotient topology. If X admits a CW structure, then also this nth symmetric product admits a CW structure. Now let us suppose that X comes with a base point. So if X is based, there is an inclusion, or rather an embedding, from Spn of X into Spn plus 1 of X. And it's just given by sending the class represented by a tuple x1 up to n, so square brackets will refer to the equivalence classes, to x1 up to xn, and then the base point in the last slot. Since we have symmetrized the action anyhow, I could also have put the base point in any other slot, and this would be the same point in the same map. So this map is a closed embedding, and I will often pretend that it's actually an inclusion, so I will consider this as a closed subspace of this via this map. Also in the space situation, we can now pass to the colimit, and then we get the infinite symmetric product. And then I'll write Sp infinity of X for this. And this is just the union of n greater or equal to 1 of Spn of X. So more formally it would be the colimit taking along these closed embeddings, but thinking of them as subspaces, it's the union with the weak topology, which is the colimit topology in here. The main classical result about this construction is the theorem of Dold-Thom, which was published in 1958 in an Annals paper, and it says that for a based connected CW complex, there is a natural isomorphism on the one hand side between the kth homotopy group of Sp infinity of X, with the base point, and this is isomorphic to the kth integral homology of the original space X, and here's k greater or equal to 1. In particular, this theorem, if we can apply it to spheres, and we get out that Sp infinity of Sm, well, the sphere only has one homology group in non-zero dimensions, and so this will only have one non-vanishing homotopy group. So the sphere SPM of Sm is an iron-bounded plate space of type Z, comma M. Because each of these functors, the SPn and also the SP infinity, is a continuous based functor in the space, we can apply it level-wise to an orthogonal spectrum, and the structure maps get carried along. You know, after all, an orthogonal spectrum is just a continuous functor from some indexing category, and we compose with another continuous functor, and then we get a new orthogonal spectrum out. We'll be particularly interested in applying this to the sphere spectrum, so we're going to evaluate the n-fold symmetric product and the infinite symmetric products on representation spheres, and we get orthogonal spectra, and then I want to simplify the notation. So I want to write Spn for Spn composed with the sphere spectrum, so this is the orthogonal spectrum whose mth term is Spn of Sb, and B varies over all inner product spaces. So this is an abuse of notation because Spn denotes both the functor and the orthogonal spectrum, but I will soon only work in the stable context and the spectrum context, and I will only consider these things. So this is for n greater or equal to 1 a natural number, and also for n equals to infinity. These closed embeddings from one symmetric product into the next symmetric product I can also apply to all these spheres, and then I get a sequence of closed embeddings of orthogonal spectra. So it starts with the sphere spectrum because Sp1 is just the identity functor. It goes to Sp2, so on. Somewhere we have Spn, we go on, and then we have Sp infinity, which is the union along these closed embeddings of orthogonal spectra. And the Dold-Thom theorem in particular implies that this is an Einberg-MacLane spectrum for Z. Non-equivariantly, that is. Einberg-MacLane spectrum for Z. You know, on the zero sphere, it's not quite a level-wise equivalence, but if you do it on the one sphere, then the map from the infinite symmetric product, which also happens to be the free abelian monoid, topological abelian monoid generated by a base space, to this, which has the model as the free abelian group, reduced, generated by a base space. This map is a weak equivalence as soon as we plug in some connected CW complex, in particular a positive dimensional sphere. So you get a morphism of orthogonal spectra from Sp infinity to the model for Hz that I've discussed at the end of the last lecture, and this is even in positive levels, it's even a level-wise equivalence. These symmetric product spectra that in some sense interpolate between the sphere spectrum and the Einberg-MacLane spectrum have received a lot of attention in non-equivariant stable homotopy theory, and they come up in all sorts of different contexts. And on the next whiteboard I want to tell you about some properties about them in some contexts in which they come up. One of the early papers with information about the stable homotopy types of the symmetric product spectra is due to Nakaoka. And I'm going to record some consequences of his paper, although they are not exactly formulated in this form in the paper. In the paper there are homology and cohomology calculations done, and I will tell you what consequences this has for the stable homotopy types. So the first result you can get out of Nakaoka's calculations is the following. For n greater or equal to and n not a prime power, so not a single prime to some power, the subquotient spectra Spn modulo Spn minus 1 is stably contractible. So these inclusions of one of the symmetric product spectra in the next, they are nice, they are H cofibrations, so the quotient actually models the mapping cone and you always get long exact sequences. So if you find out information about a subquotient, this tells you information about the map from one filtration into the next filtration. So for example, the way he derives this calculation is that he shows that the mod p cohomology for an arbitrary prime p vanishes if this is not a prime power, and the rational cohomology also vanishes, and by the Dold-Thom theorem this is in particular a connective spectrum, so a connective spectrum whose homology or cohomology in all fields vanishes is stably contractible. So this means that there's only something happening at the filtration steps where we're at the power of a prime. So what can we say then? So for n equals p to the h greater or equal to t, p some prime, then this subquotient is not stably contractible, but you can say some other things. So the first thing is that sp p to the h modulo sp p to the h minus 1 is 2 p to the h minus 3 connected. So the homotopy groups vanish up to dimension 2p to the h minus 3. And moreover, if you look at the integral homology of this, sp p to the h modulo sp p to the h minus 1 with integral coefficients, this is an FP vector space. So in particular, this spectrum is a p-torsion spectrum, but a little bit more is true. So these homology groups are not only annihilated by some power of p, they are annihilated by p itself. Moreover, he showed that the inclusion from now not a subquotient, but from a particular stage, sp to the h, into sp infinity, which is an Einberg-MacLane spectrum for z, induces a surjection on mod p cohomology. On mod p cohomology. And he explicitly describes the kernel. And there's an explicit description. So very roughly speaking, the description is as follows. On mod p cohomology, you get a surjection from the mod p cohomology here to the mod p cohomology here. But the mod p cohomology of Hz is roughly half of the mod p Steno algebra. More precisely, for example, in terms of the basis by admissible monomials, here you would have all the admissible monomials that do not involve the Bochstein. So in some sense, half of that. And he describes the kernel in terms of admissible monomials. So this gives you a very good grip on the mod p cohomology of the spectrum, and that's a very good starting point for finding out further information about this particular spectrum. So for example, you might want to run the Adams spectral sequence. I mean, we know the cohomology even as a modulo of the Steno algebra, so that's a good first input to try to make some calculations. So some consequences of this are, for example, that pi 0, which is pi 0 of the beginning, the sphere spectrum, which is just z, maps by an isomorphism to pi 0 of Spn for all n, and this maps by an isomorphism to pi 0 of Sp infinity, which is also z because this is an Einberg-MacLane spectrum. So because the subquotients are all at least one connected, all the maps in this filtration induce an isomorphism on the zeroth equivariant homotopy groups. Moreover, because the integral homology of these spectra is annihilated by a prime, in particular its torsion, the rational cohomology will also vanish of these subquotients. So this implies that all these maps in the filtration from the sphere spectrum, which is sp1 to sp2, they're all rational equivalences. All the way to sp infinity, hz. These are all rational equivalences. We knew this before for the map from all the way from the beginning, from the sphere spectrum to the Einberg-MacLane spectrum, because by Serre's calculations of the rationalized homotopy groups of spheres, in positive dimensions, all the homotopy groups here are torsion. So in particular, rationally, this only has a copy of Q in dimension 0, and this also has. So from all the beginning to the very end, we sort of knew this, but it follows now from Nakaoka's theorem that All these things in the middle are isomorphisms on rationalized stable homotopy groups or equivalently on rational homology groups. Also, because most of the subquotients, if you're not in a prime power, vanish, this means that in this sequence very often the maps are in equivalence. So at the beginning something changes because 2, 3, 4 and 5 are all powers of a single prime. You'll have different stable homotopy types, but then from sp5 to sp6 is a non-equivariant stable equivalence. Then 7 is again a prime, 8 is a prime power, 9 is a prime power, but from sp9 to sp10 you again have a stable equivalence, and so on. Another consequence of this is that because the subquotients get more highly connected, they're roughly twice as highly connected as the n is, also the map from a fixed filtration stage to the hz is roughly 2n minus a little bit connected. So in particular, you also get out that the map from Spn to Sp infinity, which is equivalent to hz, is 2n minus 3 connected. And because this is an iron-McLean spectrum, it has only a non-zero homotopy group in dimension 0. It follows from this that pi k of Spn in low dimensions we can describe. It's of course z in dimension 0. All of these are connective, so the negative homotopy groups vanish anyhow. And then it's 0 from 1 less than equal to k less than equal to 2n minus 3. So the more you go along in the filtration, the more you approximate hz, and roughly with the slope of 2. As I already mentioned, there has been a lot of work in non-equivariant stable homotopy theory where symmetric products of spheres or these subquotients come up, and I just want to mention a few of them. For example, there's work by Pritchell and Middy on stable splittings of classifying spaces of groups, and then some of the summands that come up in these stable splittings can be identified with subquotients of the symmetric product filtration. There's also work by Aron and Dwyer that relates this to the partition complex and to the Titz building, to just name a few. As I will try to explain in today's lecture, many of these things are vastly different in the equivariant situation, so there are new phenomena coming up, and the direct analogs of these statements are not true. So the equivariant situation is more complicated, or maybe you want to say it is more interesting, depending on the perspective. The symmetric product spectra Spn are given to us as orthogonal spectra. So they represent global stable homotopy types, and hence in particular a compatible family of G-equivariant stable homotopy types for every compact Lie group G. Today I want to exploit this global structure to give a very compact description of the subquotients as global homotopy types, and then I want to use this to calculate the zeroth G-equivariant homotopy groups of the SPNs. Let me start reminding you of what we already know about the extreme cases. So one of the extreme cases is n equals 1, and as I mentioned a number of times, SP1 is just a sphere spectrum, and now this is the global sphere spectrum. And we know what the zeroth equivariant homotopy groups are. Pi 0 underlined of the sphere spectrum is the Burnside ring global functor. So the global functor represented by the trivial group. If you evaluate this on finite groups, you get the Burnside ring, the Grothendieck group of isomorphism classes of finite G sets. This beginning of the filtration also tells us that we shouldn't try to calculate higher homotopy groups equivariantly, because after all, even non-equivariantly, the higher homotopy groups of the sphere spectrum are only known in small dimensions, and we will probably never know them completely in closed form. So why we shouldn't even try to calculate higher homotopy groups equivariantly if we don't know this non-equivariantly. So how about the case n equals infinity? So SP infinity admits a map to Hz. So this is this point-set level model of the Einstein-McLean spectrum that I discussed at the very end of the last lecture. This is the free abelian monoid generated by a base space. This is the free abelian group generated by a base space, and this is sort of just a map which formally adds inverses. I explained at the end of the last lecture that this is trying very hard to be an Einberg-MacLane spectrum for the constant global functor, and it actually is on finite groups, but not in general. And one of the facts is that this map is a global equivalence. So it's not only non-equivariantly the case that SP infinity is an Einberg-MacLane spectrum for Z, it's even globally the case that it's an Einberg-MacLane spectrum, but I mean in this points at level model. So it's on positive dimensional compact Lie groups, this will have non-trivial stuff in positive dimensions, non-trivial equivariant homotopy in positive dimensions. So in the general case, as I said, we don't want to look at the equivariant homotopy groups in positive dimensions, there's simply no hope to calculate them. But in pi0, we now get an interesting sequence of global functors. It starts with the Burnside ring global functor, which is pi0 underlined of sp1. Then we get to pi0 underlined of sp2, and so on. Pi0 underlined of spn. And then eventually they all map to pi0 underlined of sp infinity, which at least on finite groups is the constant global functor. So we have a naturally occurring sequence of global functors that interpolates between the Burnside ring functor, which for finite groups, for example, is a free abelian group on the number of conjugacy classes of subgroups, and it sort of ends to a single copy of Z, at least on finite groups. And so this is a naturally occurring sequence, so it should have some natural description, and that's what I want to present to you now. I will give you a presentation in the abelian category of global functors, because that is the answer which, at least to me, is the natural answer that has a nice closed form. In the next lecture, I will then expand this and also give you very concrete and explicit calculations for what pi0 upper G is for specific groups G. But for today, I want to give you this global presentation. The short answer is that in this sequence, all of these maps are epimorphisms of global functors. They're all surjective, and you get from here to the end step by killing a single relation, by dividing out by a single element, but you have to do it in a global fashion. So here's the element. We define an element Tn, and I'm going to describe it to you in two slightly different forms. So I can take the element n times 1 minus the transfer from sigma n minus 1 to sigma n of 1, and this is an element in pi0, sigma n equivariant of the sphere spectrum. So this one is the multiplicative unit, and I'm just taking n copies of it. I add it up n times. And here's an element which has sort of the same degree. I take the multiplicative unit from the smaller group, sigma n minus 1, and I transfer it up. Because the index of sigma n minus 1 in sigma n is n, and that's also the augmentation of this. This will actually lie in the augmentation ideal of the Burnside ring, as it should, because after all, the morphism from here to here is killing the augmentation ideal, at least on finite groups. So for finite groups, and sigma n is a finite group, this is equivalent to the Burnside ring. So I want to give you a presentation of this in the language of sigma n sets. So here I take n times the sigma n set with just one element, with a point. So this also means an n element set, but with trivial sigma n action. And then I subtract the sigma n set, or rather its class in the Burnside ring, of the tautological sigma n set, the numbers 1 up to n, and sigma n is permuting them. So this is an n element set with trivial action, and this is an n element set with a transitive action. They have the same number of elements, so the difference lies in the augmentation ideal. And under this correspondence between the Burnside ring and the equivariant stable homotopy group in dimension 0, this is what these elements correspond to. So now we look at the global subfunctor generated by this. Let Tn denote the global subfunctor of the Burnside ring global functor generated by Tn. And as I mentioned when we discussed the zeroth equivariant homotopy groups of little m capital O a bunch of lectures ago, by definition this means it's the smallest global subfunctor of this containing this element, and if you want to explicitly calculate it, you not only have to take this element and the free abelian group it generates in the value at sigma n, but you also have to close it up under all the global operations. So you have to take this element, hit it with all restrictions, with all transfers, keep doing that and taking the Wheeling groups generated by that. Because we have this explicit presentation of the global Burnside category, one can work out more explicitly what this global subfunctor looks like evaluated at a particular group G, and I will do that in the next lecture when we make this calculation more explicit, what it means for one group at a time. Now I can state the main result that I want to explain today. And the theorem says that the morphism of global functors from the Burnside ring global functor to pi 0 underlined of SPn, which is induced by the inclusion from the sphere spectrum into SPn and the fact that pi 0 underlined of the sphere spectrum is this. So this is surjective and it descends to an isomorphism of global functors from the quotient of the Burnside ring global functor by the subfunctor generated by this element Tn with pi 0 underlined of Spn. You might want to convince yourself, that's a simple algebraic manipulation, that the global subfunctor generated by Tn is contained in the global subfunctor generated by Tn plus 1. That's a direct consequence of the fact if you take the element Tn plus 1 and restrict it down to the group sigma n, then you get that element Tn. In the next lecture, I will make this calculation more explicit by working out what the value of this global functor at a particular group G is in terms of the subgroup structure of the group G. For working this out explicitly, you will have to know what the conjugacy classes of subgroups are, and you will have to know the relative containments and the relative indices. This will, on the same side, be a very explicit calculation, but it will also not be particularly nice or particularly easy to remember. So in my perspective, this is the nice answer, the global answer. It's this formalism that makes it nice and easy to state. So here's the proof strategy in very rough terms. So it basically has two steps. So identify the subquotients Spn modulo Spn minus 1 as suspension spectra of unreduced suspensions of certain orthogonal spaces, certain unstable global homotopy types. And these will be global classifying spaces of a particular family of subgroups of sigma n. I will explain this in more detail later. These are sort of variations of the global classifying spaces of groups. And then use the non-exact sequence. Use the end. So in dimension pi 0 and pi 1 of the non-exact sequence that you get. To inductively calculate pi 0 underlined of Spn. So to give you a little bit of a flavor already now, if you know that the subquotient is the suspension spectrum of an orthogonal space that itself is already a suspension, then because suspension spectra have no negative equivariant homotopy groups, and if the space is already itself a suspension, then the subquotient will have all pi 0 equivariant vanishing, and that's the surjectivity of this. The reference for this theorem is this paper of myself from 2017, and there you can find all the details that I have to sweep under the rug in this lecture. Here's the orthogonal space that will feature in the global identification of the subquotients of the symmetric product filtration. I define an orthogonal space that I'll call B global of Fn. And this is the global classifying space of the family of non-transitive subgroups of sigma n. And it's defined as follows. So right now, global classifying space of a family of non-transitive subgroups is just a name for this orthogonal space. It's already reminding you that it has something to do with global classifying spaces of groups, and I will tell you a little bit later why this name is well chosen. So first I define an orthogonal space that I denote S blank comma n, and I define S V comma n. V is an inner product space that is allowed to vary, and this is the space consisting of all tuples of vectors v1 up to vn in v to the n that satisfy two conditions. So first of all, they sum up to 0. Also they have unit length, so v1 squared plus vn squared is 1. And a different way to say this is the unit sphere in the kernel of the summation map. This orthogonal space at every inner product space V has an action of the symmetric group simply by permuting the entries. And it's also clearly functorial in linear isometric embeddings in V, because the linearity means that this condition is preserved, and if you have an isometry or an isometric embedding, this condition will be preserved. So because the sigma n action acts and it's compatible with stabilizing under linear isometric embeddings, we can pass to the quotient spaces, and now we can define an orthogonal space that we really want to study, B global Fn, and its value at V is simply the orbit space. It has Vn modulo sigma n with the same kind of functoriality in linear isometric embeddings here. Let me go through the very low dimensional examples of this. So the first observation is that the global classifying space of S1 is actually empty, because after all, it would consist of vectors that at the same time are 0 and have length 1, and there are no vectors that have this property. So this really starts to get interesting with a global classifying space of 2. So let's look at what this means. So by definition, this would consist of vectors VW in V squared with the property that V plus W is 0 and length V squared plus length W squared is 1. But of course, the first relation, that the sum is 0, means that one of the vectors is really negative of the other vector, and so in particular they have the same length, so we can identify this by setting W to minus V with the set or the space of all vectors V in V, such that the length of V is squared is 1/2. Under this identification, the sigma 2 action here, which swaps the two factors, becomes the sign action here. And so this is really identified with the projective space of V, because we can send the vector to the line that it spans, and then here we have to divide out by the sigma 2 action, so I forgot to write this, and because the sigma 2 action here sends a vector to minus its vector, you exactly get the projective space. But the projective space is also the same as the linear isometric embeddings from sigma, so this is the sign representation of sigma 2 into V, and then modulo the action of sigma 2. So this example we had discussed a long time ago when I talked about global classifying spaces of compact Lie groups. The sign representation is the faithful representation for the group with two elements. So this is the smallest, the preferred model of the global classifying space of the group sigma 2. So in this particular case, for n equals 2, this global classifying space of the family of non-transitive subgroups happens to be the global classifying space of the group, but that is a special feature that happens for the small number. That has to do with the fact that the only non-transitive subgroups of sigma 2 is the trivial group. Maybe I should say what a non-transitive subgroup is. So H in sigma n is non-transitive if and only if the tautological action, the H action on the set 1 up to n, you know, sigma n acts on this set tautologically, and this is a subgroup if this action is not transitive. And you can characterize this because you can clearly identify the maximal non-transitive subgroups up to conjugation. This means that H is subconjugate to a subgroup of the following form. Sigma k cross sigma n minus k for some 1 less than equal to k less than equal to n minus 1. So this is the subgroup which leaves the first k elements invariant and the last n minus k elements invariant. So this clearly is not transitive. It has 2 orbits, and you have to be, if you're not transitive, you're a subgroup of one of these or a conjugate of this. If you have a topological group, or maybe even a compact Lie group or a finite group, and you have a family of subgroups, then there's always a traditional classifying space of such a family. And this is the global version, so I'm secretly indicating that also if you're given a group and a family of subgroups, a compact Lie group and a family of subgroups, then there's a global classifying space of the family. The global classifying space of the group is the special case where the family only consists of the trivial group. And that's why these two things are the same here. Non-transitive means just you have to be trivial, whereas as soon as you have sigma 3, sigma 4, sigma 5, then there are non-transitive subgroups that are also non-trivial. So the two notions start to diverge from sigma 3 onwards. To justify the terminology, I would like to recall a fact from lecture 5, where we first talked about classifying spaces of compact Lie groups. So let me recall that if we take the global classifying space of a group G and we evaluate this at a complete K universe, so this is in general how we get at the K equivariant homotopy type represented by an orthogonal space, well, at least when the orthogonal space is closed, and all the ones we're considering today are closed. So this was linear isometric embeddings from V into UK. This is and then modulo the action of G coming from the action on V, where V was some chosen faithful G representation. And moreover, this space LV, UK, which has a commuting action of G from the source and K from the target, is a universal K times G space for a certain family of subgroups, namely for the family of graph subgroups. i.e., those closed subgroups gamma in K cross G such that gamma intersected with E times G, so we look at the part that sits in the second copy, is just the identity element. The orthogonal space B global Fn has a similar property, a somewhat related property. So by definition, B global Fn at UK, so the underlying K equivariant homotopy type that this represents, is you take the sphere in the kernel of the summation map, and then you divide out sigma n. So it's the same kind of construction. We first have a space with an action of k times sigma n, and here we had a k times g action, and then we're dividing out the sigma n action. In this situation, the g action on the source, because it was faithful, is a free action. In this situation, the sigma n action here is in general not free, so that is a difference, unless n happens to be 2, in which case it would be free. In general, it's not free. And the main justification for the name is the following proposition. The k times sigma n space you get before dividing out, so as uk, n, is also a universal space. It's a universal k times sigma n space, but now for a different family of subgroups. For the family of those closed subgroups, gamma in K cross sigma n, such that when you intersect gamma again with the second factor, in this case with sigma n, then this is a non-transitive subgroup. That's where the name comes from. It's a non-transitive subgroup of sigma n. So here the sigma n action was free, which is equivalent to the intersection with E times sigma n consisting only of the identity element. Here we're relaxing this, it's not necessarily going to be free, but if you intersect it down, it has to be a non-transitive subgroup. So it's a very similar kind of situation. We have a universal space for a family, and then we're dividing out the action, which in this case is not in general going to be free. And it's a global classifying space for this family of non-transitive subgroups because the condition we're singling out is kind of universal in the other variable. It's universal in the k variable, the k can run, but the condition always comes by intersecting with the second factor. Now I would like to explain that also the homotopy set Rep-functor that you get from B global Fn has a property that's reminiscent of the property that we have for global classifying spaces of compact Lie groups. So for this, let me recall that there was a special element that I called the unstable tautological class U sigma n lying in pi 0 sigma n of the global classifying space of sigma n. So this class is represented by the following element in L of Rn mod sigma n and then sigma n fixed points. So here I'm using r to the n as my faithful representation for sigma n, where I permute the coordinates. It's kind of a very convenient choice. Then this would be the global classifying space of sigma n evaluated at Rn, and then taking sigma n fixed points. So the orbits are formed via the sigma n action on the source, and the fixed points are then formed via the action on the target. And this is represented by a tautological element, namely the identity of Rn and then its orbit. So this is a very special element, and the global classifying space of sigma n together with this element represents the functor evaluating at sigma n. So more precisely, pi 0 underlined of the global classifying space of sigma n is isomorphic to the contrarian functor from Rep to sets that is represented by sigma n. So Rep was the category of compact Lie groups and conjugacy classes of continuous homomorphisms. The equivariant homotopy sets of an orthogonal space have a contravariant functoriality in this category. They are what I called Rep-functors, contravariant functors from Rep to sets. And in this special example, you get the represented Rep-functor, and this isomorphism is given by evaluation at this special class. Of course, that was a more general statement. You could have had a compact Lie group here in place of sigma n. The global classifying space of the family of non-transitive subgroup has a somewhat analogous property. There's also a special class which generates the Rep-functor, but in this situation it's not going to be freely generated. So here's this special element. So here's a construction. So let me first introduce an element that I call B. B stands for barycenter, and it's the vector 1 over n times. And this lies in nu n, and nu n is now my abbreviation for Rn with a coordinate permutation action by sigma n. So I'm using this when I want to consider it as a representation of sigma n. Now I introduce another element that I call dn. This is 1 over square root n minus 1 of b minus e1 all the way up to b minus en. So where does this lie? So this lies in nu n, which is already r to the n, and then n copies. And now you can see why I introduced a new notation, because it's r to the n, but the two kind of to the n's play a slightly different role. So this is a vector in r to the n in this representation. It has all the same coordinates, and I'm subtracting from this the first coordinate vector, and this makes it sum up to 0. These coordinates all sum up to 1. I'm subtracting one of the coordinates vectors, so this vector has coordinates summing up to 0, and so are all the others. So this lies in here, but it actually lies in S of nu n, comma n. I already explained why all the coordinates sum up to 0. That was one of the conditions. And this factor 1 over square root n minus 1 is exactly there to normalize it to length 1. If you go through the calculations, that's exactly the factor that you want. So now I'm going to take the sigma n orbits in this. So now I'm going to take the element dn times sigma n. It's sigma n orbit. This now lies in S of nu n, comma n modulo sigma n. And this was exactly the global classifying space of the family of non-transitive subgroups evaluated at nu n. And I'm claiming that in there it is a fixed point under the sigma n actions coming from the action of that coordinate. And that should be plausible because this whole definition was kind of symmetric in all of the n's. So this element, the sigma n orbit of dn, exactly represents an element in the equivariant homotopy set, sigma n equivariant homotopy set of this orthogonal space. And then the proposition is that the class of dn times sigma n in pi 0 sigma n equivariant of the global classifying space of Fn generates the Rep-functor pi 0 underlined of B global Fn. So this is somewhat analogous to the property that the global classifying space of the group has. Here it's freely generated by this element, it's a represented functor. Here it's only if you close up the Rep-functor under restrictions along all continuous homomorphisms you get all elements. So this is more concretely saying that a general element in pi 0 k for some group k is of the form alpha upper star applied to this special element for some homomorphism alpha, but here it's in general not freely generated, so the conjugacy class of this homomorphism is not necessarily uniquely determined. For n equals 2, this actually is freely generated because then this is the global classifying space of the group sigma 2, but when n is 3, 4, 5 and so on, then there are relations here, whereas there's no relations on this side. Now comes the key ingredient in the inductive proof of our main result, the calculation of pi 0 underlined of SPN. And this key ingredient is an isomorphism. The orthogonal spectra given by the subquotients. The orthogonal spectra SPN modulo SPN minus 1 and the suspension spectrum of B global Fn and then unreduced suspension are isomorphic. So here X diamond is the unreduced suspension. So this is X cross 0, 1. And then you're identifying X cross 0 to 1 point, say the south pole. You're identifying X cross 1 to another point, say the north pole. So this takes an unbased space and turns it into a based space where you pick either the south or the north pole as your base point. This is the unreduced suspension. We can do this functorially, so we can apply it to an orthogonal space at every level, and this gives us a based orthogonal space out. And then a based orthogonal space has a suspension spectrum, sigma infinity. And there's no plus here because I already had a base point after I did the unreduced suspension. I'm using that base point. I'm not adding a disjoint base point to this. I will now give you a sketch proof of why these two things are isomorphic. The proof will be sketchy in that I'm going to give you equivariant homeomorphisms at each level for each inner product space V, or I will indicate such equivariant homomorphisms. Of course, a full proof would require me to commit myself to specific homeomorphisms and then afterwards check that with these homeomorphisms I'm using, everything is compatible with the structure maps. That I will not do, so in this sense it's just a sketch of a proof. So here's how the argument goes. SPN modulo SPN minus 1 at some inner product space V. Well, quotients are just done level-wise, so this is SPN n of SV divided by Spn minus 1 of Sv. So this is the n-fold Cartesian product of some space, and then symmetrized. And here I'm dividing out all the things where the base point is 1 in one of the coordinates. So this is a reduced version of the n-fold symmetric product, and this has the effect that instead of Cartesian product, I could work with the smash product. So this would work for an arbitrary base space, not just for the sphere. So this is the same as taking Sv to the n-fold smash power. So here we use the Cartesian power, now it's the smash power. And then I'm dividing out the sigma n action that now permutes the smash coordinates. Now I'm going to rewrite this a little bit. You know, if I take the spheres of two representations and I smash them together, that's the same as the sphere of the orthogonal direct sum of the representations. Here I'm doing this n times, so if I smash Sv with itself n times, it's really Sv tensor Rn. So this is the sphere of Sv tensor with Rn, and then divided out by the sigma n action, and the permutation action on this side of the smash vectors here becomes the action only on R to the n, the tautological action by permuting the coordinates on that side. But now as a sigma n representation, R to the n splits up as the diagonal copy, which is a trivial copy, and the reduced version. So this splits up sigma n equivariantly as Sv direct sum V plus rho n, and by rho n I mean the kernel of the summation map, so this is the reduced natural representation of sigma n, and then the whole thing is still dividing out by sigma n. So now I split it up exactly in the way that the sigma n action on this first summand is trivial. So I can pull this out of the orbits. So this is the same as Sv smash, and then I have Sv tensor rho n modulo sigma n, and now you see the suspension spectrum coordinate popping up. That's this coordinate here. Now here, before we're taking sigma n actions, we have the one-point compactification of some representation, and the one-point compactification is always the unreduced suspension of the unit sphere. So this is isomorphic to Sv smash, and then on this side we have the unit sphere of V tensor rho n, unreduced suspension, and then mod sigma n. And this is one of the technically tricky points, because here you have to reparameterize 0, 1 to 0, infinity, and you have to do this in a careful way so that in the end everything is compatible with the structure maps. But then sigma n orbits, I can pull into the unreduced suspension, so this is Sv smash, and then S of V tensor rho n modulo sigma n. And if you remember how the global classifying space of this family was defined, I was taking n tuples of vectors that sum up to 0 and then are of unit length, but n tuples of vectors that sum up to 0 are the same as vectors in V tensor, the reduced natural representation that sums up to 0. So this is really the same as V smash B, oh, and I have forgotten the unreduced suspension, B global Fn at V, and then unreduced suspended, and this is exactly the value of this orthogonal spectrum at the inner product space V. So altogether I have indicated a sequence of homeomorphisms. The homeomorphisms are equivariant with respect to the action of O of V, and now you would have to carefully check that after pinning down isomorphisms they are compatible with the structure map, and I'm going to omit this. I would like to draw a consequence of this. Because the inclusion of one of the filtration steps, Spn-1 into Spn, is nice. It's also equivariantly evaluated at V and H cofibration. The quotients will behave like the mapping cones when it comes to equivariant homotopy groups, so we'll get a law-exact sequence of equivariant homotopy groups, either individually at some compact Lie group or as a full global functor between Spn-1, Spn, and the quotient, and we're going to substitute this now for the quotient. So now we get a long-exact sequence of homotopy groups, and I will only write down the relevant part at the lower end. So somewhere we get pi 0 underlined of Spn. This is what we inductively want to calculate. Incoming is pi 0 of Spn-1. This map is induced by the inclusion. The quotient spectrum we've identified here, so this is pi 0 underlined of the suspension spectrum of the global classifying space of Fn and then unreduced suspended. The suspension spectrum of every well-pointed orthogonal space has vanishing homotopy groups in negative dimensions, but here we're plugging in something that itself is already a suspension. And because we're not just plugging an arbitrary orthogonal space, but one which already is a suspension, this will even vanish in dimension 0. And then incoming we have pi1 underlined, the global functor, sigma infinity, E global Fn, unreduced suspension, via a boundary homomorphism. So from this identification of the subquotient, we immediately get out that this inclusion from Spn-1 into Spn on zeroth equivariant homotopy groups, it induces a surjection. This was part of the statement. Inductively, we know that we're always killing something when we go from one stage in the filtration to the next stage. It also tells us that if we want to figure out what is being killed from here to here, we have to identify the image coming in via the boundary homomorphism from this global functor. And here we're going to exploit the things that we have used before, namely this is generated by a single element. This is generated as a global functor by a single element that I'll call Wn. So let me tell you why this is the case. So first of all, I mentioned earlier that the global classifying space of the family of subgroups, while its equivariant homotopy sets don't form a free Rep-functor, the Rep-functor is generated by a single element. An exercise in an earlier lecture that you've hopefully done is that if you do a suspension spectrum, then this freely generates a global functor from the Rep-functor that you had before you suspended, at least on the level of zero equivariant homotopy groups. So the zero equivariant homotopy group global functor of a suspension spectrum is the free global functor generated by the Rep-functor of the orthogonal space you started with. And this is essentially what the statement here is saying is there's a slight complication from the fact that we have the unreduced suspension and not a proper suspension, but this sort of all works out. So there's a special element in here that comes from the generator of pi 0 sigma n of this orthogonal space that I call Wn. And if we want to understand what happens from here to here, we just have to figure out what the image of this element that generates this global functor under the boundary map is. And we get out that the kernel of the map from pi 0 Spn minus 1 to pi 0 underlined Spn is the global subfunctor generated. We apply the boundary map to this generator, which is not a free generator, but it's a generator of this global functor. So this global functor happens to be cyclic, generated by a single element. So we just have to see what the boundary map does and then generate the global functor under there. The global analysis of the subquotient of the symmetric product filtration gave us this purely algebraic payoff. We get a short exact sequence or an exact sequence of global functors at the lower end. We could deduce that this morphism is surjective, and this thing that maps in is generated as a global functor by a single element in this particular group. So we're basically done if we can figure out what the boundary map is, and this is the following result. The boundary applied to Wn is I lower star of Tn, where I is the inclusion from the sphere spectrum into Spn minus 1, and Tn is this element that was mentioned in the main result. It's n times 1 minus the transfer from sigma n minus 1 to sigma n of 1. This lies in pi 0 sigma n equivariant of the sphere spectrum. The proof of this is somewhat involved and somewhat technical, and it's too technical for me to do it on the blackboard, so I have to refer you to the paper. It is an important step though, because this is additional information. The subquotient the subquotient identification doesn't tell us what this map does. This map has the algebraic information about the attaching, how the subquotient is attached to SPn minus 1. And there's some geometric input that you have to use to work out this relation actually holds. From here, an inductive proof, inductive argument shows that A modulo the global subfunctor generated by Tn maps isomorphically to pi 0 underlined Spn straight forward. So while I do not want to give you the full proof of this relation on the blackboard, I do want to explain at least half of the relation. I do want to explain why this particular relation, this difference is certainly a non-zero element in here, but why this element actually goes to 0 when you go all the way to pi 0 underlined of Spn, which is sort of half of the containment that this implies. So I want to sketch why the element Tn in pi 0 sigma n of S maps to 0 in pi 0 sigma n of Sn. So I want to explain this Spn. This is an equality between two homotopy classes, and often such equalities are done by algebraic manipulations. But sometimes, if we're lucky, we can prove an equality of homotopy classes by actually writing down a homotopy. In this case, an equivariant homotopy between representatives, and that's what we're going to do. So I first have to tell you how these two classes are represented. So on the one hand side, the class n times 1 in, or rather its image, in pi 0 sigma n of Spn is represented by the map from S to the row n. So this was my notation for the reduced natural representation of sigma n. So these are n tuples of real numbers that sum up to 0. And this is going to be to Spn of row n. It's going to be represented by the diagonal map. So which sends an x to x, comma x n times. So this is not the inclusion where I would go x and then the base point. It's the thing which takes it n times. I don't want to formally prove this, but it's hopefully plausible because n times something, I'm taking the same thing n times. The other map was a transfer, and now we have to go back how transfers were defined. Transfers were defined by equivariant Thom-von-Triagin constructions. And if you want to do this, you have to choose an embedding, first of all, sigma n equivariantly from sigma n modulo sigma n minus 1 into some representation. And sort of the transfer from sigma n minus 1 to sigma n, we base it on the particular embedding, can be based on the sigma n embedding. So I have to choose an embedding from sigma n modulo sigma n minus 1, which I can identify sigma n equivariantly, again with a set of numbers 1 up to n with a tautological action. And I'm going to embed this exactly in this row n, the reduced natural representation. So I have to assign to a number k, I have to give you an n tuple of vectors that sum up to 0, and in such a way that the stabilizer of the image is exactly the right subgroup. And here I'm taking b minus ek in a notation that I had previously introduced. So this was this barycenter element, which has 1 over n in every tuple, and this is the kth coordinate vector. So if I write this out, this is the vector which has 1 over n in most coordinates, and in one coordinate has 1 over n minus 1. 1 over n, and this is the kth coordinate. And it's plausible, and you might want to check that this is actually a sigma n equivariant map, and it's actually an embedding, so we can base the Thom-von-Triagin construction on this embedding. And now I'm going to draw you, for n equals 3, a picture of what this embedding looks like. For illustrating the equivariant homotopy that witnesses that this class and this class have the same image when you go on to the sigma n equivariant homotopy group of Spn. For illustrating this equivariant homotopy, it will be convenient to use linear coordinates. So I use a sigma n equivariant homomorphism between the unit sphere, the one-point compactification of the reduced natural representation. So this is a sphere of dimension n-1, and the n-1 simplex with its boundary collapsed. So here's a picture for n equals 3. This is the largest that I can draw. There, this would be a 2-sphere, and I'm looking at the 2 simplex where the points are 0, 0, 1. These are the edges. 0, 1, 0, and 1, 0, 0. The sigma 3 action on this is a delta 2, and the sigma 3 action is by permuting the coordinates. And when I draw this picture, you always have to think of the whole boundary to be collapsed. The collapsed boundary is the base point at infinity in here. There are points with special isotropy under the permutation actions. So let me draw them. So there's first of all the barycenter, which is a fixed point. Under this identification, the barycenter corresponds to the point 0 in here, which is the other fixed point. So at the base point at infinity, that is the collapsed boundary. Here there's the point 0 that corresponds to the barycenter. And the other points are points with isotropic group transposition. And the rest, the interiors of these 6 little triangles, these are free points with no action. So when I choose this equivariant embedding from 1 up to n into the representation, so the images of those things would be these 3 points, like this one, and this one. And then the transfer map means is that we have to stretch out little balls around these points to the entire sphere. In these linear coordinates, I can stretch out a little bit further. So now I'm going to give you a picture of the transfer map, which is now going to be a map from this triangle to itself. The map has to send the boundary to the boundary. That's the point which has to be fixed. And what I'm doing is I'm taking this triangle and stretching it out all the way linearly to the boundary. So the transfer map is fixed on the boundary, and everything else is stretched linearly to the boundary. That's a picture of what the transfer map does in these linear coordinates. This is a picture of the transfer map on 1/3 of the triangle, but everything has to be sigma 3 equivariant anyhow, so just by flipping and rotating the picture, it tells you what it has to do on the other triangles. You know, this triangle has to be stretched out in that direction, and this triangle has to be stretched out in that direction. So that's a map of the transfer map, which goes from here to here in these linear coordinates. Now, the thing we want to show is, I'll exhibit a sigma n equivariant homotopy between 2 maps. One from the sphere of the reduced representation to SPN of the sphere of the reduced natural representation. So this was the map that sends x to x, comma, 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 x. So this is the map that represents n times 1. And the other one is when I first do the transfer, represented by this map, this linear stretching, to S rho n, and then I include into S rho n SPN of this. And this is the map that would send x to x and then base points everywhere. So that's a different map from this map. I could give you the homotopy in coordinates, in linear coordinates, but I think it's more instructive to actually show a little movie and animation of it. Here it is. The first scene shows how the barycenter moves under the homotopy. The barycenter is drawn in red, and it corresponds to the fixed point 0 in the representation sphere. The transfer takes the barycenter to the collapsed boundary of the simplex, which corresponds to the base point at infinity. At first sight, it might be surprising that the barycenter can move to the boundary in a sigma 3 equivariant fashion. And of course it cannot, because it is an isolated fixed point. But the homotopy takes place in the third symmetric product of the representation sphere, so the fat red dot represents the barycenter with triple multiplicity, i.e. 3 smaller red dots at the same place. And as an unordered configuration of 3 individual points, the triple barycenter can move to the boundary in a symmetric way. The equivariant homotopy from the entire 2 simplex is then the piecewise linear extrapolation of the movement of the configuration of barycenters. Here you see one of the three triangles that make up the 2 simplex. It is colored in dark blue, the overlay of 3 triangles in light blue. After all, the start of the homotopy sends every point to itself with threefold multiplicity. The second scene shows how one triangle moves under the homotopy. The entire homotopy is the sigma 3 equivariant extension. At the end of the homotopy, one of the 3 triangles extends over the whole simplex by the transfer, and 2 of the copies map to the boundary, i.e. the base point at infinity. So the end of the homotopy is the transfer followed by the inclusion of the representation sphere into its third symmetric product. Here's the animation one more time, now in fast motion. This completes the animated proof of the fact that these 2 elements, which are different in the sigma and equivariant homotopy groups of the spheres, actually have the same image once you go to the nth step in the symmetric product filtration. This proves one half of the containment that we need, and the other half I will delegate to the paper. This is all I was planning to say today. In the next lecture, I will make the abstract calculation in the abelian category of global functors concrete by evaluating what it says at any given compact Lie group. I will run through a bunch of examples. And I'm also planning to say something reasonable and interesting what happens rationally on higher homotopy groups if you restrict to finite groups. This is the end of today's lecture, and I thank you for your attention.